At sunrise on a cornfield in Iowa, no farmer climbs onto a tractor to guess where to plant or how much fertilizer to use. Instead, satellites, sensors, and software quietly get to work, reading the soil, measuring moisture, and predicting yield before a single seed touches the ground. This is not science fiction or a distant future. It is happening right now across the United States, where farming is becoming as much about data and precision as it is about soil and sweat. Agriculture in the United States has always been shaped by innovation, from mechanization and hybrid seeds to biotechnology and automation. Today, the next major transformation is being driven by precision agriculture and smart farming, approaches that use digital technologies to make farming more efficient, sustainable, and profitable. As pressures mount from climate change, rising input costs, labor shortages, and the need to feed a growing population, American farmers are increasingly turning to data-driven solutions to do more with less while protecting the land they depend on. Precision agriculture is based on a simple but powerful idea: fields are not uniform, and farming decisions should not treat them as if they are. Traditional farming methods often apply the same amount of seed, fertilizer, pesticides, and water across an entire field, even though soil quality, moisture levels, nutrient availability, and pest pressure can vary dramatically within just a few feet. Precision agriculture uses technologies such as GPS, geographic information systems, remote sensing, and variable rate equipment to identify these differences and manage them precisely. Smart farming builds on this foundation by integrating real-time data, automation, artificial intelligence, and connectivity to create responsive, adaptive agricultural systems. In the United States, precision agriculture has grown rapidly over the past 2 decades, particularly in large-scale row crop farming such as corn, soybeans, wheat, and cotton. GPS-guided tractors and combines were among the earliest and most widely adopted tools. These systems allow equipment to follow exact paths across fields, reducing overlaps in missed areas, saving fuel, minimizing soil compaction, and improving overall efficiency. Auto-steering technology has become common on many American farms, enabling farmers to operate machinery with remarkable accuracy even in low-visibility conditions. Another cornerstone of precision agriculture is data collection. Modern farms generate vast amounts of information from soil sensors, yield monitors, weather stations, drones, and satellites. Yield monitors installed on harvesters measure crop output in real time, creating detailed yield maps that reveal which areas of a field perform well and which struggle. Soil sensors measure moisture, temperature, and nutrient levels, helping farmers decide when and how much to irrigate or fertilize. Weather data, both local and regional, supports better planning for planting, spraying, and harvesting operations. Remote sensing technologies have become especially influential in American smart farming. Satellites and drones capture high-resolution images of fields, often using multispectral or hyperspectral cameras that can detect plant stress long before it is visible to the human eye. These images help identify nutrient deficiencies, pest infestations, disease outbreaks, and water stress at an early stage. Farmers can then take targeted action, applying inputs only where needed instead of treating entire fields uniformly. This targeted approach not only reduces costs but also minimizes environmental impacts. Variable rate technology is one of the most practical applications of precision agriculture in the United States. Using data from soil tests, yield maps, and remote sensing, farmers can adjust the rate of seeds, fertilizers, and pesticides applied across different parts of a field. For example, areas with richer soil may require less fertilizer, while poorer zones may need more or may not be economically viable to farm intensively at all. Variable rate seeding allows farmers to plant more seeds in high-yield potential zones and fewer seeds where conditions are less favorable, optimizing overall productivity. Smart farming takes these tools further by emphasizing connectivity, automation, and decision support. Internet of Things devices connect sensors, machinery, and farm management systems, allowing data to flow seamlessly across the operation. Cloud-based platforms store and analyze this data, often using artificial intelligence and machine learning algorithms to generate insights and recommendations. These systems can suggest optimal planting dates, predict yield outcomes, detect anomalies, and even automate certain decisions. Automation and robotics are becoming increasingly visible in U.S. agriculture. Autonomous tractors and robotic implements are being tested and deployed on farms, particularly in controlled environments and specialty crop production. These machines can perform tasks such as planting, spraying, weeding, and harvesting with minimal human intervention. In labor-intensive sectors like fruit, vegetable, and dairy farming, smart technologies are helping address chronic labor shortages. Robotic milking systems, for instance, allow cows to be milked automatically while collecting detailed health and productivity data for each animal. Livestock farming in the United States is also benefiting from precision and smart technologies. Precision livestock farming uses sensors, wearable devices, and monitoring systems to track animal health, behavior, and performance. In dairy operations, smart collars and ear tags monitor activity, rumination, and body temperature, enabling early detection of illness or reproductive cycles. In poultry and swine operations, environmental sensors regulate temperature, humidity, and ventilation to maintain optimal conditions, improve animal welfare, and enhance feed efficiency. One of the most significant benefits of precision agriculture and smart farming is sustainability. Agriculture is both affected by and a contributor to environmental challenges, including greenhouse gas emissions, water pollution, and soil degradation. Precision technologies help reduce these impacts by optimizing input use and improving resource efficiency. Applying fertilizers and pesticides only where and when they are needed reduces runoff into waterways and lowers emissions associated with production and application. Precision irrigation systems, such as drip irrigation combined with soil moisture sensors, conserve water while maintaining crop health, which is particularly important in water-stressed regions like California and the Southwest. Climate resilience is another critical advantage. As weather patterns become more unpredictable, U.S. farmers need tools that help them adapt quickly. Smart farming systems integrate real-time weather forecasts and historical climate data to support risk management and decision-making. Farmers can adjust planting schedules, select crop varieties, and plan irrigation and harvest operations based on more accurate predictions. Over time, data-driven insights can help farmers identify practices that improve soil health and carbon sequestration, contributing to long-term resilience. Despite its many benefits, the adoption of precision agriculture and smart farming in the United States is not without challenges. Cost remains a significant barrier, particularly for small and medium-sized farms. Advanced equipment, sensors, software subscriptions, and connectivity infrastructure can require substantial upfront investment. While large commercial farms are often better positioned to absorb these costs, smaller operations may struggle to justify the expense without clear and immediate returns. Data management and ownership are also ongoing concerns. Precision agriculture generates massive volumes of data, and farmers must navigate questions about who owns this data, how it is used, and who has access to it. Many smart farming platforms are developed by private companies, raising issues of transparency, privacy, and long-term dependence on proprietary systems. Ensuring that farmers retain control over their data and can move between platforms is an important issue for the future of the industry. Connectivity gaps pose another challenge, especially in rural areas. Reliable high-speed internet is essential for cloud-based smart farming systems, yet many parts of rural America still lack adequate broadband access. Without consistent connectivity, the full potential of real-time data analysis and automation cannot be realized. Addressing rural broadband infrastructure is therefore a critical component of expanding smart farming across the United States. Education and skills development are equally important. Precision agriculture requires farmers to interpret data, operate advanced equipment, and integrate technology into traditional farming knowledge. While many American farmers are highly innovative and adaptable, there is a learning curve associated with these tools. Universities, extension services, and industry partners play a key role in providing training, technical support, and research to ensure that farmers can use precision technologies effectively. Looking ahead, the future of precision agriculture and smart farming in the United States is likely to be shaped by continued advances in artificial intelligence, robotics, and biotechnology. Machine learning models will become more accurate as they process larger and more diverse datasets, enabling increasingly precise recommendations and predictions. Autonomous systems may become more affordable and widespread, reducing labor demands and improving operational efficiency. Integration across the entire food system, from farm to consumer, could enhance traceability, food safety, and market responsiveness. Ultimately, precision agriculture and smart farming represent a shift in how farming decisions are made. They do not replace the farmer's experience or intuition but enhance it with data, insights, and tools that support better outcomes. In the United States, Where agriculture operates at an immense scale and faces complex economic and environmental pressures, these technologies offer a path toward a more productive, sustainable, and resilient future. By embracing precision and intelligence in the field, American farmers are redefining what it means to farm in the 21st century, blending tradition with innovation to feed the nation and the world.